Hi, uh, welcome. Gokhale, can you see the shared screen?
Yes, Prakash, I can see the shared screen.
Welcome. So we are starting the session 3 of Quantum Computing Fundamentals. Myself and Professor Gokhale, both of us are here. Uh, and this is the recorded session. Uh, of the part 3, we are in the part 1, which is quantum computing and information communication aspect. And so this session 3 relates to quantum basis states represented by theta phi on a block sphere, and also we are going to discuss about eigenvectors and eigenvalues. Coming back, we do have the book which we had referred to you. Hope all of you are following the book, and we have been trying to meticulously ensure that we beforehand tell what we are covering and what we'll cover next. So this week we said, as last week, that we'll cover quantum mechanical states, superposition and measurement, basis and uncertainty principle, and the bracket operators, observable and operators, eigenvalue and eigenvectors. And then finding eigenvalue phase factor, we may differ, but at this time we'll just say that we are covering, this is the proposed coverage. So let us come to the physical aspect of quantum, which is represented by photon or an electron. Let's just take a photon. Photon is nothing but a packet of energy, which is massless in the sense that it has a zero mass, but it is a packet of light. And we call it as quantum, or packet of photon is a quantum of it. And that is one which represented can be represented in the terms of momentum of the photon, position, and its momentum. And this is with respect to time. So you can see here a sine wave and a cos wave, which is representative of the time axis and the amplitude. And the amplitude is measure of, in this case, let's say energy, and which we are keeping it uniform in this case. So assuming that, because superposition, by superposing, you can always have a increase or decrease of the energy depending on how they are represented on a mathematical positioning. So what we are saying is a photon's position and momentum with respect to time, we are trying to measure. If we measure mathematically, we can represent them by sine and cos waves. And then superposition is nothing but the combination of them in what we call state, because we represent them as a state or a vector as a summation of the state, which is said in a qubit. In a given qubit, we have a state 0 and 1, ket 0 and ket 1. So the vector psi, which represents the linear combination of the ket 0 and ket 1 state of the either the electron or the photon, they are same, and they are nothing but uh, computed on the basis of uh, the energy level. Why energy comes into picture is one of the thing is there is no certainty with, if you try to measure saying x position, then you have stopped the, you already collapsed the state to a value which is either on the 0 or on the 1, ket 0 or ket 1, or spin up, spin down, or even in terms of photon, you are when you try to measure, you have actually affected the movement of it. So basically each of these, either photon or electron, both can be represented waves as well as a mass. But for photon there is no mass, it's only energy, and it is represented in frequency by wavelength. And we say that light has a wavelength between 380 nanometer, visible range is 380 nanometer to 750 nanometer. So we represent as violet, indigo, blue, green, yellow, orange, and red, and the mass is 0 for it. But if you go by electron, electron has a electron has a what you call the mass of around 1240 nanometer, and that depends on the temperature at which you are measuring. But nevertheless, at some specific temperature, we say it is 1240 nanometer, and the computation is that you try to measure at given instance. So it could be at 0 example. At 0, here it is a 0 because it is a sine. At 0, here it is a 1, which is a cos. So basically the trigonometric value of the sine and the cos wave can be used to represent the angle of the vector. So example, angle in this case 0 degree, 30 degree, 45 degree, 60. So if you go with the block sphere which we had done last time, if you take a vector, they can be at certain angle, and those vector will have certain value at a mapping on the x or the y plane or on the z plane. So essentially what we are trying to do is to make sure that uh, if we have a photon which is sunlight is nothing but throwing photon at a distance. It comes with an energy packet. If we have a single slit, it goes through like a wave. Even though it is a particle, it is represented here as a wave because it creates that kind of a motion of the photon once it comes through one slit. But when you have two slit, double slit, then they create two waves. So you can see here I have shown waves, and these waves have a different value at different time. And so if you try to measure at one point, then it will collapse, whereas correspondingly the other end of it also wave will have its impact in a given time, and that is what it means. So there is an interference in the pattern. So you can see the pattern of here. You can see the peak is at here, even though this was the place where from it came, the peak is here. Whereas here, though, even though they are lesser than the peak here. So interference pattern can affect. And so what it means is, whenever you have a physical particle which are under 10 nanometer. Why 10 nanometer? That is because that's the time when the quantum principles start applying. Because the normal principle which we do in semiconductor, where we say that we have a gate of 21 nanometer, 25 nanometer, all that is fine. But if we go below 10 nanometer, you find that it is difficult to overcome the quantum effect. That is why you need a quantum compensation even in semiconductor. If you have a nanometer semiconductor which you have less than 10 nanometer, because the tunneling happens and it bypasses the barrier, and that means what? There is a leak. So either you call it a leak or whether you call it a tunnel, quantum tunneling, what it is essentially it means is there is an uncertainty about uh, how much uncertainty that is described by the Planck's constant. And that is, if you have x the position, p the momentum, if you take a deltas x and delta p, you multiply, then that will always be less than equal to h by 2 pi. H is a number which is represented by Planck. Planck has given that number, and that is what we saw earlier. The Planck's constant is 6.23 into 10 to the power minus 34 joule second. The joule second, because when you do h nu is nothing but the frequency. So frequency is c by f, which is what we calculate. Uh, and essentially what it means that there is a uncertainty when you try to measure the characteristics of a particle, be it a photon, be it an electron, whether it is a movement or a spin, electron spin, that is based on the magnetic field which you try to use to measure, or electric field, whichever way, whatever your measurement device is, with respect to whatever direction you have, there is going to be some uncertainty, and that is what the uncertainty principle, or we call it as uh, mm, the Heisenberg uncertainty principle. You can go and refer to this document and figure out what it is. But essentially, why I wanted to express in these two slides was that uh, everything is probabilistic in qubit sense, not like digital classical bit sense where we have either a 0 or a 1. It's not in between, or it is not any linear combination. In our case, there is a linear combination, and that is because of the nature of the subatomic particle having some kind of a quantum uh, effect, where we say that the characteristics are uncertain, and we want to take advantage of the qubit or the uncertainty of that to compute in a discrete manner. They are discrete, they are not continuous. They are discrete, but they are not discrete as in the case of our case only logical, where you have only 0 and 1. You have 0 and 1, any state in between. Therefore, the linear combination of the waves can allow us to compute parallelly many things. And that's the reason for people trying to exploit the uh, chaos of the quantum subatomic particle. With that, we'll come back to our usual representation of the quantum states, the vector states, that is ket0 and ket1 for a 1 which is aligned with z-axis in our uh, traditional way, what we call z-axis xyz Euclidean. So with respect to that, if I say z-axis, it's vertical, and then you have representation of ket0 and ket1, which we saw ket representation. So you got the psi. If it is a vector psi, you can also represent vector n or vector psi or vector anything, whatever that is we are trying to measure. Angle theta is representative of it being away from z axis, and that angle theta is what is used to represent. And if you look at the xy axis, which is a basis which is horizontal x and y in direction, those direction, that is called as azimuth. So you got a azimuth and you got a elevation. With respect to elevation, you have a theta. With respect to azimuth, you have a phi, and that can be mapped down to x and y. But you essentially, we call it as phi, the angle. And so, if you take a vector psi here in the block sphere, which is representative of one qubit. So, if I say block sphere, in the block sphere, we are representing one qubit, not two, only one. So when we say one qubit, and that is having a psi vector, and all vectors are unitary, that means they will always be on the surface. So psi is a point on the surface with a unit direction, but an angle theta with respect to z. And the state by which we measure these, are the vector space by basis which we use is ket0 and ket1, which is spin up and spin down, and that is represented as linear combination of the ket0 and ket1. These are nothing probability alpha, probability density they call it. So the probability density of alpha ket0 plus beta is a linear combination, and you can see alpha square and beta square, which is the square of the number which we are representing for the states, has to be 1, because probability is always 0 to 1 for anything. So plus there is a phase factor which is we will ignore for the time being, but for the sake of completeness, I would say that a phase factor of a complex number, because it is a complex number, it has a phase factor, like you can have an imaginary value, because these are not the Cartesian real, but these are imaginary, which is Hilbert space we call. And in that Hilbert space, what happens is then we also have to say that these can keep rotating, they can have a different theta, and therefore corresponding to that theta, you will have a complex number which is written as combination of ei theta, cos theta, uh, sine theta, etc., trigonometric, or in terms of exponential ei theta. So that theta component will be also part of phase factor. We will not be doing a lot of phase factor this time, but we'll come to phase factor as we get into circuitry in the later sessions of the courses. Going on to the next one, here I will focus mainly on the basis, that there can be multiple bases, and usually z-axis basis we call it as ket0 and ket1. If we use x axis basis on this x, we call it as plus and minus basis, and y-axis basis, we call it as I and minus I basis. All these bases are representing in their own way, in their own direction. If you do it in xy, then it will be ket plus ket minus, and eigenvector will be only be with respect to x. If you do with z ket 0, ket 1, it will only be with respect to z axis. And if you do it I minus I basis, then that will be only be with respect. So in our case, we would say that z axis is the most standard. Ket 0, ket 1, spin up, spin down is considered as the standard basis. Other basis, we call it as changed basis to evaluate any of the qubit, whether we do in elevation or azimuth. That brings us to next. If we talk about basis and bracket notation, we have to represent, we always think of a vector, and that vector has basis, and that is in the case of vector v1 represented as basis 0 and 1 is ket v1 equal to ket 1 times ket 0 plus 0 times ket 1, which is 1 and 0. So you can see 1 and 0, they are representative of a column matrix. So vector v1 is equivalent to vector r matrix. This is uh, 2 column by 1 row. So 1 row, 2. So we have here uh, 2 two rows and 1 column. So 2 by 1. Same way vector v1, now if we are representing in not ket 0, ket 1, but 1 plus minus basis, which is nothing but plus minus represents direction of x, then in that case your vector v1 will not be unitary like a 0 or a 1, but 1 by root 2. So the scaling factor has changed, and obviously the vector itself is different. It is 1 1 in this case. And we can also represent 0 and 1 basis, but if we take a 0 basis, then it will be 1 by root 2 for a plus and 1 by root 2 for minus. And same way, this is a plus ib, a minus ib. So that's a and b is 1 by root 2, 1 by root 2. So essentially what we are saying is that uh, the vector, if you want to keep the same, then you will have corresponding to that a unique representation. And this basis and bracket notations are simpler to absorb, uh, but when it comes to computation, it is always better to do matrix, and therefore you will find that uh, the duality of bracket we had discussed last time also. Here again I am pointing out that if you have a notation, let's say we call it as basis. If you have a bra basis of A, that corresponds to ket basis of A, then there is a this relation correspondence is based on the complex conjugate of bra is equivalent to complex without the conjugate of A. So this is for one basis. Now if you have a vector which is combination of vector, then we say that, hey, suppose there is a bra vector gamma, it is a combination of vector state alpha and beta, then uh, then the vector bra is similarly represented into vector, that is a ket vector, by doing the conjugates. So that means if I have a ket vector gamma, which is a combination of A with basis alpha beta, then if I want to represent the same thing in bra, it will be duality. In the sense we have to do a complex conjugate of A with bra alpha and complex conjugate B with. So basically what we are saying is when you have multiple vectors, let's say, and they want to be, you want to combine the two with bra and ket notation, this is how you do. But at the end of it, what you will get is a, in this case, we are saying that whatever you do vector v1, v2 or a, b, ultimately whatever combination of the coefficients that you use, those coefficients have to be either coming boiled down to a orthonormal basis, as we said, or they have to end up in a parallel or normal or equivalent basis. So basically, it's whatever computation you do for multiple vectors. Example, if alpha we have taken as A0 and beta B0, then the bra alpha will be complex conjugate, whereas the of A0 A1, whereas beta will be bra beta will be B0 B1 ket basis. There are no there are no complex conjugates in case of um, kits, but if you do in terms of bra, there will be complex conjugate, and corresponding to that, if you take the combination of that, this is alpha beta and beta alpha. Either way you do, but the combination will turn out to be multiplication of A0 B0 A0. Like example, since we took this as A0 A1, we just go ahead and multiply this way, either A0 star with B0 and A0 A1 star with B1. So basically it is a matrix multiplication, and this way, same way here, we'll have B0 conjugate with A0, B1 conjugate with A1. That's what it is. So whether you do map alpha to beta or beta to alpha, the numbers will be different, conjugates will be different, but at the end of it, when you want to get, either it is 0 or it is 1. If they are orthonormal, then it is 0. If they are not orthonormal, then they are 1, because for us, when we talk of bracket notation for quantum, we are dealing only with unitary matrix, and that is the reason for this conclusion. Otherwise, if you go by any other method, it will be some scalar. Essentially, we want to make sure it is scalar, and we normalize the scalar. So if lambda, if you say v1 by v2 and you get a lambda of something that is vector, then the lambda is a scalar, so you'll have to divide by scalar to normalize to be able to get a unit vector in the block sphere. So now let's go to, with this I'll switch to observables and operators. So what we have done is we have just understood what is bracket notation and how is it related to vector, how it is related to basis, and now we have to come to a new paradigm, which is observables, and for observables we use generally operators. So before we get to operators, what is observables? So when we observe, that means we should be able to measure. And when we want to measure, we want to measure which is uh, measurable, in the sense which we know. If we try to measure without a unit, you will not know what it is. So what is the unit of measurement in this case? It will be the state. And what are the state? Given a vector, there will be a ket 0 and ket 1. So physical interpretation of that is nothing but a position, momentum, or spin of an electron, example. So those are the observables. So when you have a quantum subatomic particle and you want to measure them, you have to be having some observables, and those observables are interpreted as states, are state transformations. So in this case, we are talking of a position or movement of a photon or a spin of an electron, whichever characteristic you choose, because this is mathematics is the quantum mathematics is independent of what you use in the physical sense. But when it comes to measurements, we have to rely on the physical aspects of it. So if I am finding an electron is in a position, how do I know that it is in that position? So we have to use a detector. So what detector? We will have an electron detector. So if an electron detector it strikes, then we know that electron is in that position. What is the position? Suppose it comes out to be a position which is showing 1.10 minus 10 in XYZ axis, example, in real sense, then that is what the uh, vector, or that is the ket representation. Ket representation abstract, it can be 0, 1, it can be theta phi, but we try to use ket 0 and ket 1 for up and down. So if I know that I am looking at detecting a electron which is spinning up, then how do I know that it is spinning up? And that is by using either a magnetic field which is which is an electron detector, and which is pointing out that it is moving to a lower energy. If it is moving to lower energy, I represent as uh, uh, what you call K0. And if it is going to a higher energy, in the sense, that means it is falling. Like in water, when we say it floats, if it is lighter, if it is um, um, if it is higher in weight, then it will go down. Same way, we say K0 represents the lightness of it, and so that means it is having a energy which is low, and therefore it is up, going up, whereas that is spin up, and spin down is the lower energy to higher energy. So lower, it is either collapses to lower energy K0 or higher energy, which is K1. So either way, that is the electron spin representation. See, same way we can do with photon, but then there will be a horizontal, what you call polarization, vertical polarization, and it has to go by polarization mechanism. But all the same, they can also be represented by K0 and K1, and that may be based on the momentum of the photon. That is, photon is moving which direction, whether horizontal or vertical, and accordingly we can change the basis states and represent them. So uh, the superposition is always there because they are at the quantum subatomic particle level. You do not expect them to be independent in the nanometer range, and even the atom and the uh, electron and the photon, all that are in the very very what do you call, very narrow range. And there is a phenomena which occurs, which is because of the leaks and the interferences and all that, we tend to use the basis depending on what computation problem or communication problem we are trying to solve, and accordingly adjust the basis. But in general, uh, standard basis to use K0 and K1, spin up and spin down, and it can be anything, it can be different, but then you have to specify what you are doing. And in general, the uh, quantum which we describe here, quantum state, we say that uh, it is represented by an operator. Now, what is an operator? I'll talk later, or will let Professor Gokhale go into the detail. But in general, a operator operates on a vector. So if you have a vector, there is an equivalent operator, and that will transform that vector from one state to another state. And that, in the case of block sphere or in case of quantum being a system, so if you have a one qubit system which is represented by one uh, block sphere, and if you have another qubit represented by another block sphere, and they are in two different worlds, we are not mixing them until we get to entanglement. Right now, we are only talking of one quantum bit, one Q sphere, one block sphere, and within that block sphere, the rotation of the vector is the equivalent of transformation. So if I say I have transformed a vector uh, which is having a theta to angle theta plus uh, say 10, that is, if it was in 30-degree angle and made it 40-degree angle, that means I have transformed that. And this transformation can be only be obtained through specific operators. Those are unique to whether it is in the x direction, y direction, and z direction. There is a matrix called polymetrics, which you will hear later, but that is what represents your transformation. And if I am talking of a z direction, I can these are represented by some vector, and those are called eigenvectors and corresponding values, which is uh, eigenvalues of that matrix. And actual details, I'll leave it to Professor Gokhale to present. But one thing I want to, before I close, I want to say that the quantum measurement, there is a postulate, and that postulate says that whenever you want to measure, that means you want to observe. When you want to observe, you have to measure, and if you have to measure, there is an operator, so you need to have operators. So there are specific matrices or matrices that act on the state space, and they, the probability of the measurement is what results in a particular measurement. So to put it this way, M happens, it's a probability of being M. And so if you have multiple matrices and multiple vectors for the same qubit representation, vector psi, that is, if you are representing psi vector, then you have to make sure that all the observation you do a summation of them, uh, and ensure that you are normalizing with probability. Probabilities has to be 1. So therefore, some of those probabilities must be 1. So whatever measurements you take of the psi, whether it is a bra basis, Ket basis, and then the matrices which are there, you operate on them to arrive at a probability, and that probability has to be 1. So if you have a psi and you transform it to Ket psi, then what measurements happen can be taken and summed and divided by the sum of the probabilities, and then that will give you the completeness. That means the outcome cannot be done by measuring one partial thing and then say this is the ket 0 ket 1 basis. Then you have to have at least ket 0 measurement, ket 1. So basically you have to have completeness, you must have all probabilities computed and normalized. And that is what the quantum measurement postulate states, that given an operator, the measurements that you take, they must all be computed and they should be summed basis that the probability density of it is 1. And then only you can arrive at a measurement stating this is a ket 0 or whatever collapse state you reach is on a qubit basis. And I think with that, I will hand over to Professor Gokhale, but here I will have to stop because or pause before I can hand over to him. Gokhale, one sec. So I don't have a pause. What do you want me to do? Hold it.
Yeah,
I'll just stop
no,
sharing. Yeah,
yeah,
let me
you
stop
stop
sharing.
sharing. Yeah.
Yeah, that is the best. So I have stopped sharing, I think. Can you take over?
Yeah, I'm taking over. Let me share the screen.
Oh,
Okay.
yeah. Gokhale shared, right? Yeah, go
Yeah.
ahead.
Okay. So thank you, Prakash. So quickly, let me get on to the slideshow mode. And I have a very small topic to discuss today, and I'll be quickly taking you through why we have to understand these two basic terms called as the eigenvalues and the eigenvectors. Uh, Technically speaking, if you pick up any book or any discourse in mathematics, especially towards linear algebra and matrices, they have a different type of a treatment. They talk in terms of eigenvalue, eigenvectors as a operation that you perform on a 2 by 2 or a n by n matrix in such a manner that after you perform some transformation or some operation, the, the structure of the vector still remains the same, right? So let us understand why we are doing this as well in the context of a quantum space. So first and foremost thing is we will say that we have an operator, right? That operator typically, like we have seen, could be that sigma z operator, the sigma z operator, and that operator operates on a vector. Now that particular vector could be typically our ket 0 or ket 1, the spin up or the spin down type of a vector. And if this operator operates on that, obviously it is going to transform the state, right? So in general, what we can say is all these operators transform a quantum vector state, and this will result in a transformed vector once again in the same hyperspace, whatever is the hyperspace we are discussing. And if at all I denote this in the form of a very simple matrix notation, then I define this operator. Now this operator is pretty very important. We have basically a 2 by 2 operator, and that operates on this so-called vector. This vector could be my ket0 or ket1, and then there could be a resultant vector. So if at all I say that this is my x vector and this is my a vector operator, so a operator operating on the x vector results to me a resultant vector which is x prime. Okay, that is basically the fundamental concept of an operation. So what we now do is something like this. Let us say I take my sigma, let's say my basically the operator. This operator is now denoted as sigma z, right? What is that sigma z? Sigma z is along the z axis. Typically, talking about the measurements of the electronic spin along the z direction, right? So this is supposed to be giving me some idea about the representation of the so-called measured energy. And once again, when we start coding this matrix, there is a small notation which we also have to understand here. The notation signifies each and every element in this 2 by 2 matrix, and it is identified by the position, and this is the row number and the column number index starting from 0. So obviously, when I talk about row number 0, column number 1, it refers to this particular cell in specific notation, right? So this is once again, we are going to use this whenever we put up a small Python code a little later on. So we will take this operator. So this operator is called as the sigma z operator. And then we will talk about the measurable outputs. What are the two measurable outputs? The spin up and the spin down, or ket0 and ket1. Now this ket0, ket1 are denoted by this column vectors. So now I say, okay, let us start operating. So I take this measurable vectors, operate using this sigma z, the operator. So this is what I say in a sigma z operator. And the moment I do that, obviously I can now perform a very simple matrix multiplication and then find out the resultant. The resultant is this particular resultant vector. So transformed vector. And if I say this, my transformed vector is absolutely identical to the original vector here. Okay, so this transformed vector is once again just nothing but ket0 only. Similarly, if I take ket1, the spin down, once again same operator, now operating on this column vector 0, 1 that denotes, let us say, spin down. And if I do this matrix multiplication, you will see the fact that the resultant would be once again the same column, excepting for the fact that the magnitude is different. So I can now denote this as equivalent to -1 times the same vector, right? So this is a typical fundamental nature of one type of a transformation. So what is the transformation that is happening? I have got an operator operating on a vector in such a manner that it yields to me the same vector, but probably it is scaled. Now, that scaling factor is essentially either scaled down or scaled up, and that scaling factor normally would be a scalar constant. Okay, so my observation is this: by doing this operation, my vectors are unchanged, but they are only scaled by +1 here and -1 here. Okay, this gives me what are called as the modified states. So these two basic states which are there, my spin up and spin down, are called as the eigenstates. And for what? These are the eigenstates for the specific operator called as sigma z. And what are the sigma z? Sigma z will have its own eigenspins. We call these eigenspins as 1 and -1, the 1 and the -1. Or maybe in a different terminology, instead of calling them as eigenstates and eigenspins, we can also call them as eigenvectors and eigenvalues. Okay, so I can now say that 1 0 and 0 1 corresponding to the spin up and spin down are the eigenvectors for the matrix sigma z. Please understand, these are the two eigenvectors only for this particular matrix. Incidentally, if at all you try to do and evaluate or operate these basis vectors on, let us say, sigma x or sigma y, you would not be finding these as the eigenvectors. Okay, and having said that, correspondingly you also have got the eigenvalues. And what are the eigenvalues? 1 and -1. Remember the constant values which are there, that is also called as a eigenvalues. So when you pick up any reference book, when you try to look at the fundamental conceptual definition of eigenstates and eigenvectors, you'll normally see this, right? So if at all I have got the vector x operated by a matrix A, remember now this matrix A is called as an operator working on this vector x. Sometimes you call this also as a function. This performs a transformation in such a manner that it yields to me a resultant vector x, which is multiplied by some scaling factor lambda. So this lambda scaling factor is a constant. This is called as an eigenvector, and this x being unchanged now is called as an eigenvector. Okay, so which also means the fact that for a given eigenvector I can find out an appropriate operator, or for a given operator I can also identify what could be an eigenvector. So both ways, you can computationally try to find it out. Okay, why are we doing this? This eigenvector and eigenvalue essentially also tells you what is your operator and what are your observables you are considering. Okay, so your observables could be on, let's say, sigma z, and the moment you talk about the observables being along sigma z, that means what you are trying to observe for cat 0 and cat 1. So that is typically what you have to have a idea about what you are trying to observe. And the moment you have that, then the eigenvalues of the so-called specific, let's say the sigma z, that is what? That is a matrix, that is the operator, essentially corresponds to the possible energy level that is observable in an experiment. Please understand, it does not actually evaluate to the energy level, but it is a possible energy level which is observable in an experiment, number one. And the eigenvectors typically relate to the so-called the wave functions, and these eigenvectors, because they correspond to the wave functions, you can possibly move a little ahead to find out what exactly is the phase difference between the two, the angle theta that we spoke earlier on. Discussion about phase etc is slated for a subsequent lecture of the future. Okay, so that's why we normally use this eigenvector and eigenvalues as a means of observability. So just continuing this, what we said now, I have got this operator, the sigma z, denoted by let's say 1 0 0 minus 1, which automatically and actually corresponds to the so-called measurement of electronic spin along the z-axis. Right? Understand, this is once again a probabilistic aspect of measurement of this electronic spin along the z-axis. And I'm now trying to measure the two outputs. What are the two outputs? Ket 0 and Ket 1. Right? Ket 0 and Ket 1. And if I just operate on this, obviously what the same math which we did earlier on tells me the fact that these are basically my eigenvalues and eigenvectors. So Ket 0, Ket 1 happen to be the eigenvectors for the operator sigma z, and plus 1 and minus 1 happen to be the eigenvalues. Right? What does this also mean? Let us also quickly understand some aspects in terms of trying to use this mechanism, right, of evaluating the eigenvector eigenvalues for sigma z when I try to align myself, probably let's say along sigma x. What would happen? Okay, so here is a small exercise which was there in the book as well. So let us try to perform an operation on this left right, right, or left arrow and a right arrow. Okay, so what we will do is we will try to identify what happens when I perform an operation on the left arrow and the right arrow, for which what we will try to do initially, we will try to represent this left arrow and the right arrow in terms of Ket 0 and Ket 1, because our focus is basically on Ket 0 and Ket 1, and having known the fact that I've got Ket 0 and Ket 1, I've got sigma z, right? Sigma z is now the actual operator. So we will use the same sigma z operator and try to operate on this, let us say, the left arrow and the right arrow. So what I do is, first and foremost thing, because my point of view is different. Earlier I was having a point of view which is along the spin along the z-axis. Now I am now looking at a point of view of spin probably along the x-axis. What I do is I will try to represent that as a linear combination of ket zeros and ket ones. And we had this. So I can now just say the plus and minus are what they are going to be decomposed. It will be 1 under root of ket 0 plus 1 of ket 1. So if at all I just enlarge this and represent that, then I'll have 1 over under root of 2. This will be my column vector of 1, 1. Similarly, if at all I try to represent ket minus 1 on an equivalence, I will get this as 1 over under root 2, and this column vector would be 1 minus 1. So what is this? This is basically just nothing but the ket plus and ket minus scaled according to the representation for the ket 0 and ket 1. And with this, let us see if at all I can now find out whether this plus minus have some eigenvectors in the context of sigma z. So for that, we will start off with this vector, which is my plus vector, and then I take this operator. Remember, what is this operator? This operator is my sigma z operator, and then I operate over, let's say, this ket plus. Let's say ket plus. So this is the value of ket plus, and the moment I do that, I expand this, I will get this as ket minus. So what is happening? This ket plus gets transformed to ket minus. Similarly, if I take ket minus, right, I just repeat the same operation, it gets transformed to ket plus. So what is happening here? Here, the sigma z is an operator, but in the context of, let us say, sigma x notations, or in the context of left arrow, right arrow kets, this does not prove to be the eigenvalues. So, which also means the fact that the eigenvalues for sigma z happen to be ket 0, ket 1. And similarly, if you talk about the ket left arrow, ket right arrow, obviously they probably would be referring to being the eigenvector for maybe sigma x. Okay, so in extending that, we can just say the fact that let's say the plus and the minus, which are the eigenvectors for the operator, and this will now be corresponding to the measurement of electronic spin in the x direction. And this, if at all we represent it as a sigma x, and we know the fact that sigma x in matrix form will be 0, 1, 1, 0, and this is once again in the 0, 1 basis. If at all you use this, then you can definitely prove that your ket plus and ket minus will become the eigenvectors for sigma x. So what we try to conclude is, depending upon what you are trying to observe, depending upon what is your basis vectors, right? What is your basis? If you look at, let's say, sigma z, the eigenvectors will always be your ket 0 and ket 1. If you look at sigma x, the eigenvectors will always be ket plus and ket minus. If you look at the sigma y, then automatically it will be your minus I and plus I, or ket of minus I and ket of plus I. So eigenvectors are essentially a very nice and a simple way by which you can do a measurement, and that particular measurement would be a probabilistic type of a measurement. Obviously, you are going to use an appropriate sensor, and those sensors will actually tell you, and at that particular point of time, the state of the qubit will collapse to either a 0 or a 1. Okay, so that is one of the reasons why we understand this concept of eigenvalue, and then you have got Python giving you the support for evaluating this eigenvalues and eigenvectors. I'll just show you a quick demo in the meantime. So let me share my notebook. Give me a minute. Okay, I'm just reconnecting. This is the session 3 notebook, and we are having two very simple programs that I'm going to discuss. The first one is about normalizing. Last time we were talking about the normalizing. We did not do that. So I'll just talk about what is meant by normalization. See, whenever you talk about even your Cartesian space or any vector, the vector and especially if at all you have either a cross product or some sort of an operation that you perform on the vector will either scale up and it could be of any particular magnitude and so on and so forth. Okay, so what we need to do is something like this. When we talk about this quantum domain, you have to perform all unitary operations, for which you have to ensure the fact that all these vectors are brought down to a magnitude of equal to 1. Okay, so let me take up a small example of what that possibly means. Okay, so let us say I'm talking about a very simple case here. So let us say I have got some vector here. So let's say this is my vector v. Okay, this is my vector v, and this particular vector v will typically have its as we know vector va and another vector vb. These are the two components. Let's say vb. And let us say I've got vector A, this magnitude to be equal to 4 and this magnitude to be equal to 3, and I can calculate what will be the magnitude of this. So obviously the magnitude of this will be under root of 4 square plus 3 square, right? So that will be under root of 25, so this will be equal to 5. So that is the magnitude. And the moment we talk about normalizing, all I need to do is what this vector has to be brought down to a magnitude equal to, let us say, 5. So what I do is this will be divided by 5. And not only that, even this also will be divided by 5 and this also will be divided by 5. So by normalizing, I'm going to make this as 0.8 and this now becomes your 0.6. Right? So all vectors will be definitely confined to be within my unitary type of a space. So that is basically what is meant by normalizing. Okay, so we have got normalizing that can be readily done using this normalize method in your linear algebra module in Python. So let me quickly show you the code. So we are defining a very simple vector v1, and that particular vector will print it out, and then I just perform this v1 upon, remember we have to divide that, so I just identify the normalizing value and then that value is what I take and then divide v1 into that, and that will be the resultant normalized vector which I can print it out. Right, pretty very simple. So let us take this to 1 as the input and I execute that cell, and what I do get out over here is this is the original vector 2 1, and after normalization I got this as 0.89 this and 0.44. Okay, so here now you notice the fact that the entire vector is now normalized to be within the unitary space. After having done that, I just wanted to check out if the normalization is indeed correct. So as a confirmation, what I do is I'll just take a dot product of V2 over itself, and that should result to be equal to nearly equal to 1. Exactly, it might not be there because of these numeric computations. There would be a slight error out there. So if at all you look at that, the vector dot product you will see will be equal to 0.9999, which is nearly equal to 1. Right. So that means that the vector is indeed actually normalized, and this is also true even if you want to take a complex vector. So here I just uncomment this statement and now you have got v1 which is my a complex vector, and the thing is the same, absolutely the same. So if at all I run this cell, okay, you just see once again I will have a display of this complex vector, and this is now normalized, and when I just take up the dot product of that, so I just once again see this will be my value. All right, and this the dot product obviously will give me a real number, a scalar quantity. So the imaginary part would be equal to 0. Okay, so that was about normalization. Sorry, I'll knock this off. And when we want to find out the eigenvectors, we will just take this small example of 0, -1, 1, 0. This typically could be a very simple array that got set up, and this is a complex array. I display this array, and then to evaluate the eigenvector, I just use this EIG function. That's also a part of this linear algebra module. So I just say np dot linear algebra linal dot eig, and then pass on this array. And the moment I do that, the eigenvalues and the eigenvectors, both of them are evaluated. That is what my function does, and then I just print it out. As simple as that. Okay, so quickly let us execute that. My cell gets executed, and now you see this is my original array. Okay, and the eigenvalues are 1 0j minus 1 0j. Okay, so please understand these are my eigenvalues, and what are the eigenvectors? These are my eigenvectors. Okay, so what I mean to say is, you just very quickly you can evaluate these eigenvalues as well as the eigenvectors as a means of trying to identify a possible energy state of a quantum unit. So this can also be implemented in a Python simulation. Okay, so that is all I have got for the demonstration, and let me quickly go forward here. A bunch of references are given. So this is a basic reference for the book, and then in case you want to quickly read up about bracket notations and bracket operators, you have a reference link here. And if at all you want to look at what exactly is the way the photon behaves in the context of a quantum environment, you can download these sort of articles, very interesting reads. And if at all you want to once again go through this Heisenberg's uncertainty principle a little more in detail, you can just follow this particular link. So here are some references for you, and these are some problems which are there listed directly from the book. You can try them out by hand as well. Okay, so you have got once again office hours at the regular time. I'm sorry, the date has not been modified, and this week the office hours will be I do not know, what are the office hours? Every Tuesday I think will be office hours. Yeah, here, sorry, every Wednesday 8:30 p.m. PDT you have got the office hours as well. Okay, so next week we are going to cover the concepts of what is meant by quantum computing from a computing point of view. Okay, so far we have just gone through the basic understanding about what makes up the quantum, the notation, the type of representation in terms of vectors and different spaces. And next week onwards, we'll actually jump into quantum computing. Thank you. And in case you have any questions, you can either put it onto the chat boxes, or probably you can just set up a mail, or you can just wait for this office hours. Thank you very much.
Thank you, Mr. Bhupendra. And yeah, last when you represented X notation, that was a not gate representation. So we do have
Okay.
gate representation.
Yeah. Thanks for the correction. Yeah. Yeah.
That
Thanks.
I just
Yeah.
wanted to. Yeah. I think
Thank
we'll
you so much.
close the recording here and stopping the
Yeah.
recording. Thank you.